speaker, János Kollár. János grew up in Hungary and studied first in Budapest and briefly also with Manin and Iskovsky in Moscow. He then applied to study for a doctorate in Moscow but failed his politics examination. So he was prevented from studying where he wanted to study. And as usual in these matters, the Eastern Bloc's loss was the United States' gain. So János went to Brandeis, got his PhD in 1984 under the supervision of Matsusaka, then went to Harvard and eventually settled in Utah, where he built a powerhouse of higher dimensional birational geometry with many students, postdocs, friends, rivals, some of whom are here today. He moved to Princeton in 1999, where he's now a Donner Professor of Science. So János worked widely within and around algebraic geometry, initially in higher dimensional algebraic geometry and the minimal model program. His very influential papers and books with Mori in particular and many others. Then he worked on rational connectedness, rationality questions, introducing characteristic P ideas into rationality questions. And his work has also touched on singularity theory, low-dimensional topology, and several other fields. He's been an ICM speaker twice and received other numerous awards and honors, some of which are listed. But I think all I'd say now is a big welcome to János. His title is Celestial Surfaces.
That's okay. Thank you very much. So I think that you will see a certain progression in the topics of the talks during this day. The first talk, it covered all of mathematics and physics. Then the second talk, it covered an important area in differential geometry. Whereas I just want to tell you that I found a nice seashell and I found it interesting and I just want to show it to you. Okay? So it will be easier. Yes, and so there will be a few pictures which, as you will see, are completely beyond my ability to make. So these are the people who contributed it. And so the first question you might have about the talk: what is a celestial surface? Well, as a first approximation, you can think about it as a cyclid. Now, some of you might not know what a cyclid is, but luckily here you can consult the local authority, which is Oxford English Dictionary. And in the 1896 edition, when you look up cyclid, then it says it's the envelope of a sphere whose center moves on a fixed quadratic and which cuts a fixed sphere orthogonally. And so, well, I think our standards really came down. So this was written for sort of, the general, well-educated English public. And I still cannot completely decode this definition. It seemed to have been very helpful to people. And so the new edition, it reproduces this and just mentioned that it hasn't been updated since 1896, which I understand. Okay, now, then if you come from the German tradition and then you see that Felix Klein, great encyclopedia, it devotes 60 pages to the topic of cyclids. Now the whole encyclopedia is about 6,000 pages, so maybe 60 out of it is relatively small, but still it's a substantial amount. Okay, and so let's see. Okay, so then let's go now to my definition of what a celestial surface is. Well, it's just a surface in some higher dimensional space. I mean, classically a surface in space that contains at least two circles through a general point. Okay, and so then the question is, well, can we understand all of these surfaces, or describe them and what's happening with them? Okay, now then, so this sounds very differential geometric. So why would an algebraic geometer be interested in it? Because it seems fairly easy to prove that the surface that contains at least two algebraic curves through a general point is in fact locally algebraic. And so it can be so for instance, the surface of a polyhedron is like that. I mean, it's locally just a plane. So it's made up out of algebraic pieces. Essentially, we can just sort of glue various algebraic surfaces together along their intersection lines. And so that means that the really interesting case is when we look at algebraic surfaces where there are at least two circles through a general point. Okay, and so I keep saying general point because, of course, sometimes the circles, they might degenerate into pairs of lines or double lines. So I just sort of don't want to say this all the time. Okay, now the first person who actually looked at maybe some example was Dupin, and then more seriously, Kummer was thinking about it, but I think it was Darboux who sort of more systematically tried to understand these surfaces, and he worked out lots and lots of examples. And a lot of it is treated in the book by Coolidge, a treatise on the circle and the sphere, which was actually published by Oxford University Press. And Coolidge at the time was chairman of the math department at Harvard. So it seems it was a really interesting topic about 100 years ago. People really were thinking about it. Now, if you step back a little bit, then you can ask a simpler question: what are the surfaces when there are at least two lines through every point or every general point? And so this is well known. These are just the planes or the one-sheeted hyperboloid. Yeah. So these are the examples, and so then there are some real-life examples here. So it seems that the people who started to look at cyclids recently, they worked at some architecture schools. So their main interest was in getting some nice architectural forms out of this, and so some of the pictures, they will be buildings that utilize cyclids, or at least the same principle. And so I believe this is the control tower at the Kobe airport, and then if I'm right, then this is in Sydney, maybe a TV tower. It's again, you can see the two sets of lines. Okay, now then, let's look at the examples of celestial surfaces. So now we are moving more complicated. But the planes, of course, there are lots of circles through any point, and also the spheres. Again, there are lots of circles. Now, well, are there some more? Well, and the claim is that in fact quadrics are like that. Now, of course, you have to think about this a little bit. I mean, is this true? And so, for instance, the simplest quadric is just a round cylinder. And I mean, you see sort of one set of circles in it, if you just sort of slice it like this perpendicularly. So where are the other circles? Well, maybe this is a degenerate example, but you know that if you have a cylinder, a salami, if you slice it sideways, you get nice ellipses. Now you can think about it, or try it next time if you have a salami, but you start with an elliptic salami. Yeah? So the normal cross sections are ellipses. And so you can get this by buying an ordinary salami and sitting at it, sitting on it. And now then the claim is that there are exactly two ways of slicing an elliptic salami, that the slices will be circles. Okay? So if there is a rotational symmetry that somehow these two families collide, but as soon as you have a quadric that does not have rotational symmetry, then there are two families of circles in it. Well, if you want some numerical examples, then they are here, and you see, so there's the problem that if A equals B, which exactly corresponds to a rotational symmetry, then the plus or minus doesn't do anything. So that means that the two families of circles coincide. Now, let's see what's the theoretical reason of this. Why do you expect a quadric to have two families of circles? Okay. Now, so if I have Rn with coordinates x1 through xn, I can embed it into projective n space, and then there's the ideal quadric at infinity. Sum of the xi square equals 0. So that sits at infinity. And now, it's rather easy computation that a conic is a circle if and only if it meets the ideal quadric at 2 points. So the ideal quadric has codimension 2, so that means the general conic does not meet it, but you can but sometimes it meets it at 2 points. Now let's look at the quadric in P3. Well, it's a degree 2 surface, and then there's the conic at infinity, the ideal conic, and you expect the degree 2 surface meets a conic all together at 4 points. Now the ideal conic, it has no real points. That means you get two conjugate point pairs at infinity. Now if you look at it as one conjugate point pair, and you look at the family of real planes that pass through them, then they intersect the quadric surface. Well, in degree 2 curves, they are conics, and there are those two intersection points with the ideal quadric at infinity. And so that means that there are two directions such that the parallel plane sections with this, they are just circles. Okay? So here there is some nice set of example. Okay, so I just said this is the way they come. Okay, now here there's another well-known example of a surface with two sets of circles in it, and there's the torus. Yeah, you just start with a circle in the plane and you rotate it around. Well, then there's a circle that moves, and then any point here sweeps out a circle. So here are the circles on the torus. Okay, now this is sort of a side the direction may be more interested to algebraic geometry. As well, I told you that these are algebraic surfaces, yeah? That we are looking at algebraic surfaces, and so the torus is some algebraic surface. Actually, yesterday I gave it as a homework to the algebraic geometry section to tell me what kind of surface is it in our standard language of algebraic geometry. And so again, my guess is this is a question that 100 years ago every algebraic geometer would have known the answer right away. And now I actually asked it earlier at an algebraic geometry conference. There were 150 people in the room, and actually nobody knew what kind of algebraic surface the torus is. So it's just interesting. I will tell you a little bit later. Okay, now maybe the next question is, so it actually might not occur to you, well, are there more circles on the torus? So we found already two families. Are there more? Now this is again a very classical topic, but first here there's a soothing picture of the torus. If the previous one was sort of too colorful, you can think about it. Are there more circles there? And it turns out that there are. They are called the Villarceau circle, after Captain Antoine Joseph François Yvon Villarceau, who found them in 1848. And you see here they are. Yeah? So that there are two more sets of circles on the torus. On the other hand, it turns out to be it's not as new, because in the Strasbourg Cathedral, something from around 1300, so let's see, which is the laser pointer. So it is not those on the top, but actually these lines, yeah? So these are here is the torus, and there are 3 of the Villarso circles, I believe, illustrated. So they probably should not be called Villarso circles, but we don't know who made these. And so, yeah. Okay, and so now, of course, once you have sort of here, you have 4 families of circles on the torus. You might ask, well, are there some more? Yeah. And now it turns out that on the torus there are exactly these 4 families of circles, no more. But you again might become suspicious the same way as when you had quadrics with rotational symmetry. They had fewer circles than you would have expected. You would expect 2 families on a quadric, but the rotational symmetry it killed, or sort of 2 united. So maybe there should be more if you just bump your torus a little bit, and if you work a little bit on bumping the torus, then you start getting pictures like this where there are 6 circles through every point. So here is one picture. If you like a more psychedelic version, it is here. Again, you get here 6 families of circles on these surfaces, and it's really, they pass through every point. And you see there that here for instance the 2 yellow families, they are in fact homotopic, and so when it becomes a torus, then the 2 yellows become just one, and the same with the orange families. It becomes the torus, and these 2 families here just unite, but sort of the others they stay different. Okay, so now let's try to now think about it, do some algebraic geometry, and at least let's try to see if we can get some algebraic surfaces with 6 families of conics on them. And then later we will worry whether we can make the conics into actual circles. Okay. So we start with a quadric surface, which will be just for us the real picture of it will be the one-sheeted hyperparaboloid, and I pick just 4 general points of them. There will be a little algebraic geometry here, and then I come back to some other things. And so if sort of these don't mean too much to you, then just sleep for 2 minutes and then just wake up. So then we just blow up 4 points. And now then it turns out that there are then 16 smooth rational curves of that, so isomorphic to the Riemann sphere, whose self-intersection is -1. So it is really sort of best to look here at the complex picture, yeah, where this quadric is a 4 manifold, and so I have an S2 in it, and the normal bundle has a complex structure, so so it has a joint class. I would like it to have -1. And now this 16 are rather 4 that I get from just blowing up points. Yeah, so I have the 4 exceptional curves that gives me 4 -1 curve. Now then, so each of these PIs there are 2 lines passing. Now these lines have the normal bundle is just trivial. If I blow up the point, it drops the normal bundle degree by 1. So that means I get 8. And now what's harder to see, that if I have a conic that passes through 3 of these points, then again, after blowing up, you get something that has normal bundle -1. So there are these 16 -1 curves. And you can assemble actually 10 families of conics out of these, okay? So, well, so where are these? So there are the two families of lines that exist on the hyperboloid. Now then, if you have conics that pass through two of the points, that also becomes a family of conics. And now it was the hardest to see that if there are some degree 3 rational curves in 3 space that pass through all of the points, they in fact give me, they give us two more families, okay? And so that's nice. Now it would seem to you that then you can get actually maybe 10 families of circles. So why don't we get 10 over the reals? Well, we would like to get something like a compact surface. And so that means a compact surface, it should not have actual lines. It should. So that means that the 16 lines, they should exist over the complex numbers, or they should come in just conjugate pairs, okay? And so what happens? I start with just the one-sheeted hyperboloid, rp1 plus rp1. And now, so here comes the problem that cuts down the number, that instead of blowing up here 4 real points, I have to blow up 2 conjugate pairs of complex points. So that means that the 6 families of real conics will be, but the 2 families of lines, they give me them. But then to be real, the conics that pass through 2 of the blown up points, they have to pass through a conjugate pair of points. So they can pass through P1 and P1 bar, or P3 and P3 bar, but not some other their combination. And so here I lose 4, and then the 2 families of to be listed cubics, they're there, they're nice, and real. So this gives me the 6 families of conics. Now the question is, well, will there be actually conics or circles? And well, it depends exactly how I embed this surface into 3 space. So I have to think about this a little bit. Let's see. Okay, so maybe now I should tell you the torus is as an algebraic surface. Okay, so actually at least the normalization, the technical name is, it's a degree 4 del Pezzo surface with 4 double points. So I hope that all algebraic geometers figure this out. Well, so how can you parameterize the torus? Well, I mean, just follow its construction. So you start with 2 circles, and so I said to start with 1 circle. That will be the circle of radius 8. That's the first circle, and the second circle that represents the rotation. And then how do I map this into 3 space? Yeah. And so then you see that this circle is centered at the origin, so I just translate it by B. So now it's a circle of radius A centered at the point B comma 0. And then I put U and V here that represents the rotation, and then the last coordinate, whatever this y coordinate has become Z. Okay? And so if I do it projectively, that's like this. And now you can see that sort of these 4 degree 2 polynomials, they all vanish at these 4 points. So these are then the 4 points that I need to blow up, okay? So then these are the points that I blow up. Now where do I get the singularities? That these 4 points, let's see, yeah. And so here I have P1 cross P1, and I blew up the 4 points. They sit in a very symmetric configuration, and then so these lines in fact are mapped to to just points. Each of them is mapped to a point. That's how I get the 4 singular points. And now, as you see that the natural way to do that, in fact, there is one more degree 2 polynomial that vanishes at these 4 points, and this is wx. And if I add wx here as last, then I map in the 4-dimensional projective space. So that's where this thing naturally lives. And if you are in 4-dimensional projective space, then you see in fact so both rotations as symmetry. If you just realize it as a torus, you lost one of the rotational symmetries. But in 4 space, you see both of the symmetries, and then you're just projecting it into 3 space. And now, if you follow this construction, then see here I use the very special configuration of 4 points, the intersection of these lines. If you move these 4 points into general position, then you get those examples with the 6 families of circles. Yeah. Okay, now there are some more examples of surfaces with 2 families of circles on them, so just that you see that they are in fact in large numbers. Okay. Now, then there are some real-life examples that my architecture colleagues told me about. So all of these examples are sort of a little bit with cheating. So because these various lines are not exactly circles, but sort of they try to follow sort of the same pattern. I believe this is in Glasgow. This is the Viceroy Hotel in Abu Dhabi. You see those lines very nicely. National Theatre in Beijing, and I believe this is the King's Cross station. I hope to see it on I think Saturday. So here there are maybe 3 sets of more or less conic looking curve. I don't think they're actual hyperbolas, these lines, but more or less they look conics. Okay, now here there are some computer generated images again, and well, if you are into American politics, you appreciate that I have both red and blue pictures to appear neutral. Okay. And so, yes. So then, as I told you, the classification of these surfaces was started by Dupin and taken up seriously by Kummer and Darboux. And more recently, about 20 years ago, some more examples that were not known to Darboux were found by Potman and Zoubet. And then in this series of papers, they derived the completeness of the lists of these surfaces in R3 and R4. So, and I think so. Now we have them in all dimensions. Actually, it's not that much harder. And I mean, the most interesting is probably RC. Okay, so now again, so let's start to go back to some algebraic geometry. So then you ask in general that if you have an algebraic surface with at least 2 conics through a general point, then what are they? So it turns out that this was essentially contained in some unpublished notes of Cauchy from 1999, but the person who actually wrote down this list was Shiho in 2001, and so if you sort of don't know what these are, they are not particularly interesting. There are two cases I would like to focus on, and they are below. The Veronese surface, and so you start with P2, and then you look on the degree to polynomials in sort of 3 variables. If you treat them as homogeneous, there are 6 of them, so they map P2 into to P5. That's the Veronese surface, and then there's a double Zegre embedding of P1 cross P1. So again P1 cross P1, and you look at sort of the normal Zegre embedding. You look at polynomials that are homogeneous of degree 1 in both sets of variables. But here we are interested in polynomials that are homogeneous of degree 2 in both sets of variables. So that embeds P1 cross P1 into to P8. And now you see then where will be the conics. If I have any line in P2, then since I map it by degree 2 polynomial, then the image of any line will be just a conic. So that means that this will be an interesting surface in P5, where there are in fact infinitely many conics through arbitrary points. And then the question will be, well, if I choose this embedding thing more carefully from the real point of view, well, can I arrange that these conics actually become circles? And then in the Zegre embedding, well, in P1 cross P1 there are 2 families of lines, but these become 2 families of conics under the embedding. Okay, so now maybe there's another case that's reasonably well known, and I think I want to just focus here on this example. And so it's a degree 3 surface inside P3. And then, well, you might have learned at some point that a degree 3 surface in P3 that contains 27 lines. Yeah? So now if you just take any of these lines and you run a plane through it, now a plane intersects this degree C surface in a degree C curve. But it contains this line, so degree 1 is already accounted for. The remainder is just a conic. So that means that on a degree 3 surface that has 27 real lines, and there are examples like that, there are in fact 27 real families of conics. You see, this is a really huge number, and I don't have a good picture of it, or any picture. Well, it turns out that you can make only 6 of them actually circles. So that there will not be a surface with 27 circles through a general point. Actually. Yeah. Okay, and so then there are if you know what the Pezzo surfaces are, this is an interesting list. Otherwise, this is the only example. Okay, so now let's now try to approach this question: do we have circles or do we have conics? And now see, for algebraic geometers, that's a very hard this distinction. So we are used to working over the complex numbers, and we typically don't have a metric. So that means the degree of a curve is a very good invariant to us, or the genus of a curve is, but whether it's a circle or an ellipse usually is not a question that makes sense to an algebraic geometer. But luckily, there is a classical theorem here that helps us. And now, many people are using the word classical theorem to refer to something that's fairly recent, but this is in fact a classical theorem. So it was proved by Hipparchus, something like, what is it, 2,200 years ago nearly, okay? And then there was a modern treatment was given by Halley, which says that the stereographic projection is conformal, okay? So now, and so what is the stereographic projection? That you have a sphere and you put the plane through the equator, and then you stand at the North Pole, or maybe look at the South Pole, if you like. You look and you just look at a point on the surface of the sphere, and you go until you hit the plane. And now, what's actually quite remarkable about it, that if you have a circle on the sphere, then its image will be a circle in the plane. You see, if you sort of just have a circle in three space, and the image is almost always an ellipse. But sort of that's the remarkable thing is that here the circle on the sphere becomes a circle on the plane, and conversely. Now, why is this very, very useful for us? Because so we are interested in some surface that's contained in RC, and I would like to understand the circles in it. Now, let's look at the inverse image of it under the stereographic projection. Well, then I have a surface inside Sn, and then it still contains now circles. Now, but what's nice about circles, about Sn, that the conic that's contained inside the sphere is automatically a circle. Why? Because the conic is contained in a plane, and if I intersect a sphere with a plane, well, then I get a lower dimensional sphere. If the dimension is right, then I get a circle. And so that means that once I'm in the sphere, then it's enough if I find conics there, because they are then automatically circles. So that means that the really natural place to look at this question is not in surfaces in just Rn, but surfaces inside Sn, okay? And then just count the families of conics that are contained there, okay? And so now then, how do we translate this into algebraic geometry? So that means I want to understand here some real algebraic surfaces that are contained in the real n-sphere that have at least two real families of conics. Now, then of course, once we are here, we don't need to ask this over the reals. We can ask this over an arbitrary field. So for instance, over the field of rational numbers, that I have an arbitrary quadratic hypersurface. So it's defined by this degree two polynomials in the variables x1, x1, xn plus 1. And then I would like to understand the surfaces in it that contains at least two families of conics. Well, let's go on translating the algebraic geometry, because I told you that the most interesting cases are when just P2 is just mapped by the degree 2 polynomials somewhere. And so in general, if I have two algebraic varieties, P and X, then I can look at the space of maps from P to X, and since I want to fix the degree, it's a nice invariant. Let's look at the maps that are given by degree 2 polynomials. So that this means that the algebraic geometry question that I have now, I fix a field, and a quadratic hypersurface, and then I would like to describe the spaces, the degree 2 maps of P2 that land into that quadratic hypersurface. So then, back in my original question, if I solve it over the reals, this will give me the surfaces that contain a 2-dimensional family of circles through each point. And the other is if I have P1 cross P1, and again I want to look at the degree 2 maps into the quadrics, and these will give actually sort of more sort of new examples of surfaces with 2 one-dimensional families of circles. Okay, and so there are a few more cases where the method that works, but in general it's very hard to describe spaces of maps like this, but in this case it will work. Now, because this completely algebraically, and maybe here again I'm interested in, yes, I will treat the second case more carefully. So I just start with some quadratic form, and then I want to find some polynomials pi in 2 variables. And here I think I wrote this inhomogeneously. So these are just degree 2 polynomials. They are not homogeneous. And so then I just want to find solutions where the xi's are just degree 2 polynomials over the field. So this will then correspond to the mapping of P2 into this quadratic. Okay, now then in algebraic geometry usually the question is easiest over the complex number. So it turns out it's the same over any algebraically the closed field. So what I'm especially interested is the Veronese as the degree 2 maps. And now it turns out that this space, the set of degree 2 maps from P2 to a smooth 4-dimensional quadratic, turns out that's the most interesting case. That has altogether 5 components. Okay. Now there are 2 components where the image is just the Veronese the embedding, but it turns out there are sort of 2 ways the Veronese can sit inside the smooth 4-dimensional quadratic. Then there is another component where the image in fact sits inside the 4-dimensional linear subspace. So this is very special. It's a singular projection of the Veronese surface, and in fact it's a special projection. It turns out that it's singular along a line. A general projection of the Veronese into 4 space will just have a unique singular point, but these are special projections. They are singular along a line. And then there are maybe the least interesting cases, the quadruple plane. And so the image is in fact just a plane, but I have a degree 4 map to some plane that's contained inside Q4. So that's very, very interesting. Okay, now before I can state what happens over an arbitrary field, well, we need some terminology on quadratic form. So if I have this 4-dimensional quadratic that's defined in a degree 2 homogeneous polynomial in 6 variables, let's call this x0, x5. Now, then this has a discriminant, the discriminant of Q6. Now for us it's defined only up to squares, because geometrically if I multiply Q6 by a constant, I get the same hypersurface. So the discriminant is defined up to a square. Now, then there's a width reduction theorem, which says that if your quadratic it has a point over your field, then you can split off two variables as x4 times x5, and then remain just something of three variables, and maybe you can repeat it a few times, and so then when there are no solutions left, that's called the anisotropic kernel. And there is a special case, sort of the easiest to deal with is a split form, x0, x1 plus x2, x3 plus x4, 4x5. Okay, and so now then the case that we are interested in from the point of view of celestial surfaces, then here the quadratic, well, I just have the equation of the sphere that has discriminant -1 is anisotropic kernel, it has rank 4, and it is non-split. Okay, so then let's see what the solutions are, and the most interesting is to understand the Veronese the components, and sort of I told you that there are two components. They both have dimension 20. They are essentially just P20, at least they are birational to it. But you see, sometimes they are defined over your field, and sometimes they are conjugate. So it turns out they correspond to the values plus or minus the square root of minus the discriminant. So I told you in the sphere case, we are interested the discriminant was -1, so that means I get 2 points, I get 2 actual components like this. Okay, so then that means that there are sort of two ways of arranging that the Veronese surface sits inside the sphere. Okay, now of course you might say that sort of the Veronese that the quadratic has a large automorphism group. So you might say that maybe we should be interested in these maps only up to the automorphism group of the quadratic. And it turns out that the answer here is in fact very nice. There is a theorem. I could not find an actual reference to it in the literature, but probably it was known to Scorza and Semple around 1920s. So it's included as an exercise in the book Semple and Roth from 1949, but he gives no hints. A modern treatment was given by Ayman Shepard Baron, and it says that that you are interested in a four-dimensional quadratic that contains a Veronese surface. Okay, well, then what you can do is you can blow up the Veronese surface, and you can contract them all the secant lines. So these are lines that are contained in the quadratic that intersect the Veronese in at least 2 points. And now it turns out that if you do this, then the quadratic, it becomes just a P4, and then the secant lines, they all together, they map to just a curve. It's a degree 4 rational normal curve. And so actually something very interesting thing is going on here, because beforehand what had the Veronese surface, well, that was unique, that's just P2. But then the quadrics, especially if you are working over some fields like the rational, there are lots of different quadrics, and so that means we had something like a fixed surface that's contained in some variable quadric. Now then, on the other side of this picture, well, the ambient space became just P4. It is really actually P4, and then what changes? That just this rational normal curve. Now, what's a rational normal curve? So if you live over the complex number, that just you take the line and you map it into 4 space by the degree 4 polynomials. Now, of course, here we are maybe over an arbitrary field. So what you should think that you have a plane conic and you map it into 4 space by degree 2 polynomials. And so that means that up to isomorphism, these rational normal curve, they are the same as the conic in the plane. So that means that it's a quadratic form in just 3 variables. So somehow this thing we started with a quadratic form in 6 variables, and now in the end answer we have just a quadratic form in 3 variables that tells us everything about this situation. So maybe I want to go to the algebraic version of this. Yes. Okay. So this is a completely algebraic version of this statement. You start with a 6 variable non-degenerate quadratic form, and you are asking whether it has solutions of the form where the xi's, they are degree 2 homogeneous polynomials in just 2 variables. And I mean the general case is, and so I have here 6 of them, where the vector space of this degree 2 polynomials in 3 variables has dimension 6. So the general case is when these are completely independent. And now then the answer is that you can find a solution if and only if this Q6, you can write it in this very special form, so x0, x5 plus x1 square and so on. And it turns out then up to the automorphisms of the quadric, there's a unique solution, and so here is a, oops, sorry. Yes, so there's a unique solution, and so to try to give you sort of the simplest solution, maybe this is not it. Okay, then let's see. I think maybe I should stop here, and then there is some time for questions, maybe if the